Good day, everyone. My name is Aruni Azizah from the Faculty of Computer Science, Universitas Indonesia. Today, I would like to present a research entitled An Introductory Study on Image Quality of Dehazed Images by myself, my colleagues Laksmita Rahadianti from the Faculty of Computer Science, Universitas Indonesia, and Hilda Deborah from the Department of Computer Science, Norwegian University of Science and Technology. This will be the outline of my talk today, which consists of four main parts. I will begin with the introduction. Digital image formation involves the process of traveling light rays that are reflected by objects and then captured by camera. It is assumed that the scene is situated in a clear media, ensuring the light traveling freely, as seen in the right image. Unfortunately, this is invalid in many real-world situations. That is, when the surrounding media contains microparticles that interfere with the traveling light rays, such as fog and haze. These situations are referred as scattering media. An image captured in scattering media is shown on the left image, which we will refer to as hazy images. As you can see, hazy images suffers from blurring, detail occlusion, additive scattering noise, and loss of intensity. In order to understand more about hazy images, let's have a look at the model of hazy image formation. Suppose there is an object located d distance from a camera in a scattering media. The image I that will be captured by the camera consists of two parts, as shown by the equation. The first part, J, original intensity, times T, comes from the light rays traveling in the air, reflected off the object and captured by the camera. The second part comes from the light rays around the object that are obstructed by microparticles, and thus scattered. Based on this equation, it seems obvious that the clear image J could be recovered by substituting values of the variables in the equation, that is, beta and D. However, this information is most likely not available, making it an ill-posed problem. So, why is it important to dehaze an image? In image processing, it is difficult to understand a hazy scene, especially for computer vision methods that heavily rely on visual cues. A clear image is certainly useful for accurate feature extraction. For these reasons and others, multiple methods have been proposed to perform image dehazing. Research on image dehazing has been conducted and many approaches have been proposed. However, the dehazed images are of varying levels of quality and it's difficult to benchmark their perceived quality. This is because hazy images do not usually come with their corresponding clear image as required by image quality assessment or IQA methods. As a result, assessment of these images is largely based on human perception, that is, determining if it is a visually pleasing image or not. However, this brings us to another discussion as to what can be categorized as visually pleasing based on human perception. In order to contribute research on this particular problem, we conducted an introductory study on image dehazing and tried to identify problems that appear during image dehazing. We compared two image dehazing methods where one is a deep learning model and the other is an image enhancement method. They were chosen due to their widespread usage. The image dehazing is then followed by an objective and subjective image quality assessment. And based on this study, we hope it will open a discussion on what aspects must be considered when performing image dehazing. From this section, I will explain the experimental setup of this research starting from datasets. We collected 45 hazy outdoor images from the OHAZE dataset and 30 images from the dense haze dataset, which are images with denser and more homogeneous haze. These datasets are outdoor images. Clear and hazy images were captured by camera, whereas the scattering media was generated by a fog machine nearby. Every scene contains objects, including a Macbeth color checker. In total, we obtained 75 hazy clear image pairs. Because we use a deep learning model, 60 image pairs were used as a training set and the other 15 as a test set, which we will refer to as test set A. We also obtained hazy images from the University of Texas Live Image Corpus, which consists of hazy images captured in various conditions and do not have corresponding clear images. We obtained 5 hazy images from this source as a test set, which we will refer to as test set B. The first method is the pix-to-pix generative adversarial network by Isola et al. This model was proposed for image-to-image translation in various domains. We intend to translate hazy images to the correct clear image using this model. The implementation is used as is, as well as its setup and hyperparameters. We trained the pix-to-pix model using the training set and then tested with all test sets. Pix-to-pix relies on training images to learn the translation between hazy and clear images. Thus, the result of translating test set A might have an advantage since it comes from the same source as the training set. This makes test set B interesting for the analysis of pix-to-pix dehazing. The second method is the contrast-limited adaptive histogram equalization, or CLAHE. We chose CLAHE because hazy images can suffer from low contrast, and various dehazing image works have claimed that human visual system is actually more sensitive towards contrast. We use CLAHE to dehaze images of test set A and B by running a Python script, also setting a parameter, the clip limit, to 2. The Python script will first convert the RGB hazy image to the LAB color space and divide the images into 64 tiles. Once CLAHE is applied on each tile, the image will be converted back to an RGB image. IQA is employed to evaluate results of dehazing. The first one is an objective IQA, where each dehazed image is directly compared to its corresponding ground truth. That is why only test set A image results were evaluated. In this research, 5 IQ metrics were computed using MATLAB scripts, where the first one is the delta EAB color difference. It calculates the color difference between two images in the LAB color space. The second metric is the delta E 2000 color difference, which is a refined definition of the previous formula. Both values ranges from 0 to 100, with 2.3 as its just noticeable difference. In our research, we normalize these values to the range from 0 to 1 for an easier comparison. The third one is MSE, that returns a number that describes the deviation of image data ranging from 0 to 1. SSIM describes the perceptual difference of two images, where its value ranges from -1 to 1. And PSNR measures the ratio of signal to noise in an image, and the value ranges from 0 and above. The color difference metrics and MSE are error values, which means lower values indicate better quality. SSIM and PSNR show similarity, which means higher values indicate better quality. The second evaluation is subjective IQA, following the protocols of psychovisual experiments. Our research requires observers to compare 20 pairs of dehazed images from both testing sets. All images were placed in a specific arrangement, shown in this image. Each image set were displayed digitally, and observers were asked to choose which dehazed image was perceived as visually pleasing. Observers were also allowed to give their additional thoughts about the dehazed images on this psychovisual experiment. A total of 30 observers were able to participate. This slide displays three sets of images from test set A. From the results of dehazing test set A, Pix2Pix is able to reconstruct a consistent haze-free corresponding image, whereas Clay-He, although it cannot eliminate the haze entirely, is able to reduce the haze significantly, hence producing an image with better contrast. In the case of dense haze, Clay-He is unable to completely dehaze the image, likely due to the haze effects completely saturating the intensity captured by camera, removing the original intensity of the scene. In this case, Clay-He is not able to reconstruct the scene, although Pix2Pix has learned how to estimate this missing information. Still about images with denser haze, even though Pix2Pix has learned to estimate lost information, it is still unable to reconstruct image details in certain areas, as evident in displayed images. Additionally, there is an artifact in image test set A number 14, in which the Macbeth color checker was constructed twice. This shows that the Pix2Pix results being somewhat unnatural compared to its ground truth. These images are the result of dehazing test set B. Clay-He is able to give a more natural dehazed image despite still appearing hazy. In the case of obtaining absolute clear image, this is not ideal. These examples and the previous ones display the main weakness of Pix2Pix model. Our trained model has adapted to the color scheme and appearance of the training data sets, thus unable to dehaze test set B naturally, since it comes from a different data source and may produce strange effects such as unnaturally dark skies areas in test set B2 and 4. This section displays results of objective IQA, where the metrics computed and average values are calculated. According to the figure, color difference is negligible and just under the normalized, just noticeable difference. Pix2Pix was able to reproduce the color scheme of the dataset, hence the lower error. Same can be said for MSE. The SSIM is relatively good for both dehazed results, although still need improvement. Overall, Pix2Pix model performs better than Clay-He on test set A. However, for a more general solution, it is necessary to use a different method. This section displays the result of the subjective IQA, where the graph represents how many observers preferred Pix2Pix dehazed images versus Clay-He ones in all test sets. Pix2Pix dehazed images scores higher only for test set A. For test set B, despite still retaining haze, most observers agreed that Clay-He produces more visually pleasing images. This shows that human observers might have picked up on unnatural dehazing that occurred in Pix2Pix dehazed images. An interesting result is obtained for test set A image number 8, where the preference score is almost tied. In conclusion, image dehazing by Pix2Pix show a good estimation of the corresponding clear image. However, the results are very much reliant on the training set. Meanwhile, Clay-He is sufficient for light haze scenes, but unable to dehaze an image with denser haze due to oversaturation. In other words, in our research at least, Pix2Pix dehazing method is a good solution for specific data sets, but a poor general solution, whereas Clay-He is more suitable because common daily situations are more likely to have light haze. Lastly, both methods used in this paper are not yet able to solve the problem of dehazing completely. As for our possible future works, later on, the context of dehazing must be taken into consideration. That is, depending on the end goal, we must determine if the image result must be an exact reconstruction or lenient to errors. Moreover, specific features of images that are picked by observers must be investigated further. An in-depth study into the human visual system is also necessary to assess the visual criteria and preferences. An objective and subjective inquiry must also be conducted on the difference of contrast, color balance, naturalness and saturation, details and structure, and many more. And this is the end of my presentation. Thank you for your attention and have a good day.